Okay. So today we're going to kind of look at some how index of refraction plays in with what you observe. So when you look at how light interacts with different mediums as it goes from like one to another. So if I take, say for example, this glass, and I take this pen, and I put that in there, depending upon your angle. So if you look at this, when it's in this glass, you'll notice that the bottom part looks a little bit bigger than the barrel up there at the top. Now think this through. If that happens, what do you know about the magnification of whatever's happening at the bottom part?
Greater than
A
1.
little bit greater than 1, not vastly, it doesn't look like it's huge, but however that light is going through there, and again, as you go through this, listen to me, you have to think through where the light starts and where the light ends up. So if I hold this up, that light is, the photons are starting there, it's hitting the pen is bouncing that light off, it's going through the glass, and then it's ending up in my eyeball, okay? So something has to be happening to that light as it goes from the glass out, okay? Because it doesn't look the same. So since this is a little bit bigger, so what that tells me is that light, instead of going straight through, it's almost acting like a concave lens because it's taking that light and it's diverging it a little bit. So one option is that that light gets diverged. Another option is that, well, maybe that light gets converged. But as you go through this, and you want to go through the math, you have to look at where the light is starting and where it's ending up. So we're going to go out to the fish tank, and I'll show you this in just a second. So here's what's going to happen. So typically what happens is that you have like a point source, okay? It's like a light, an object that's reflecting the light off of it. Something is emanating the light source. Now here's what's going to be important. The light is coming from here and it's going out, okay? So here's where index of refraction becomes important. So out here you have air, which has an index of refraction of 1. Here you have glass, which has an index of refraction of 1.33. So when that light, okay, transitions from that glass out into the air, so we're looking at that transition from this point out to here. What's it going to do when it hits that air? Is it going to be get down, or is it going to get bent up? Down or up?
Down.
What'd you say, Jacob?
Down.
Why?
Because the outside is going to move faster because the air, if light moves faster, the air is going to curve that way.
That's right. So imagine this is going back to that wheel and axle analogy. So we're going from 1.33, it's traveling slower. That's like we got 5 inches of snow. Here you're going on to dry pavement. By the way, everybody's asking, when's the test over optics? I don't know, because I don't know what's going to happen Wednesday. So it's going to be sometime early next week. I just don't know, because I don't know what's going to happen on Wednesday. But then, unfortunately, then you're into parent-teacher conferences, and I don't want you to get, I don't want to give you guys a test the first day back after, even if we have school on Wednesday, like after a 4-day break, because you all are going to forget everything that I taught you. So the test is going to be next week. I just don't know when yet. Okay. So if you want to plan ahead, there you go. Okay. So this thing is going to come out like this. It's going to transition from this glass out to here. This side is going to speed up. Boom. It's going to come down like this. Now, is the same thing going to happen with a ray of light coming up like this? So when this comes out, what's it gonna do? Bend up, down, up, because this side's gonna speed up, so it's gonna push that up like this. So this is where your eyes play tricks on you. So if you trace this out, because this line, when it transition, goes up like this, and this is going to go like this. So this is a very creepily drawn eyeball, but there's your eye. Okay, your eye is picking this up. Your eye tries to reconstruct where it thinks this light is emanating from. So when your eye sees this, your eye traces it to a point in front, because your eye can't see what's happening back here. It can only see that light as it passes through that medium. So what happens is that when I look at that, okay, it's going to look like it's actually closer than what it actually is, because of the fact that that light, when it goes out to that less optical dense medium, speeds up, it gets bent, you're here, okay? Now, this equation is not on your equation sheet. So I don't know why, it's one of the standard equations of all optics. So what this does is that it tells you, hey, here's your image distance. This is what this is going to appear as. Sometimes you'll see this written as N2 over N1. Sometimes you'll see it as N over N0. The idea being is that this is where you start, this is where you finish. And then, and I had to kind of squeeze this in, and then you multiply that by the object distance, okay? So here's how this is going to play out. So here you have glass which has an index of refraction of 1.33. That's where that started. It's ending up out there with a value of 1. So in this situation, I'm going to take 1 and divide that by 1.33, and the actual distance behind that thing is 10 centimeters. Okay? So if you do the math on this, you get, I think it's like 7.5.
Yeah.
So what that tells me is that this object is going to appear to be only 7.5 centimeters in front of the glass. In reality, it's 10 centimeters. So this is why if you ever go like spear fishing and you're standing and you're trying to stab something in the water, that's tough because the depth is going to be off. So here's what's going to be important here. The source of that light is going to bounce off here. It's going to be maybe a bulb, something that's reflecting that light. But it's starting here and it's going out. Now, in contrast to that, we're going to reverse it. So now we're going to have a glass wall. And now you're going to be the fish. Oh, got a little crazy with the eyelashes on that one. Let's back off the eyelashes. Okay. And you're looking at the outside coming in. So now, you're the fish. And you're looking at something that's emanating light out here. So, when this comes in, you're going to go from an index of refraction of 1 to an index of refraction of 1.33. Okay? So, when it hits this more optically dense medium, which direction is it going to get bent? Closer to the center, further away?
Closer to the center.
Closer to the center. So this light, when it goes through here, is going to get bent closer to the center because it's going to hit this, slow down. This side's going to slow down. Top's going to slow down first. It's going to hit this, boom, get bent. Now, with this one, you'll notice that the light, what you're going to see, is going to work the opposite way. So what you see, what your mind tries to recreate, is an image that's further away. Because when you're looking at it, what you're seeing is this. You see the light coming like this. And you're going to reconstruct it and go, oh, that's going to be way out there. So it's the exact same idea. It's the exact same equation. So the only thing that differs is that now this thing is going to start at 1.33 because that's where it's going to go. And it's going to end up out there at 1. And if we use that same distance as 10 centimeters, you get 13.3 centimeters. So if you're here, if you're the fish, and you look out, things are going to appear further away than they actually are. If you are outside looking in at the fish, because it's bouncing off, the light is bouncing off the fish are actually going to appear closer than they actually are. Okay? See the difference between the two. You have to keep in mind which direction that light is going, how it's getting bent, and how that's going to impact what your mind tries to recreate. Got that idea? Okay. So, Danny, bring the camera and we'll try and pull this off.
Okay.
I'm not sure if we can, but we're going to try it. So, let's go to the back. Stop.